All right, so picking up right where we left off, we are trying to find I of t. I guess I didn't undo this piece here. I already tried to make this video once and kind of made a mistake, so I had to redo it. But we're trying to find I of t here. So what I'm going to do is I'm going to move what we've already done kind of over, and I'm going to resize it so that we have some space to work. Recall that we kind of figured out that we need to just use Ohm's law, but the problem here is we need to divide this Vs of t divided by this impedance, and we have our Vs is a function of time and our impedance is a complex value. How in the world are we going to take the quotient of those two things? Well, what we need to do is we need to get them in the same form. And if you remember from what I had shown previously when we talked about phasors, we can write time domain expressions like this one as phasors, because we know that the frequency in our circuit isn't going to change. We talked about how the only things that we care about are the magnitude and the phase, which I have as 0 here, right? It would be out here as plus 0, but we know that it's 0 because I don't have it written. So I can just write my Vs of t, this function, I can rewrite it as, you know, big Vs is I kind of how they do it in the book. They just use it as like a bold capital Vs. It's going to be 5 angle 0. Where 5 represents my amplitude of the sine wave and 0 represents my phase. Okay, well that's good, but that still doesn't get us anywhere because my impedance is a complex number. Well, recall that my complex number, x plus jy, can be converted into a phasor, right? Where r is equal to the square root of x squared plus y squared, and phi is equal to the tan inverse of y over x, right? So I can take my impedance and convert that to a phasor, and my voltage is also going to be represented as a phasor, and then I can do V divided by Z because I showed that dividing two phasors is really easy. If you recall from a few slides ago, I guess it was a lot of slides ago, but I showed that dividing two phasors is just as easy as taking the ratio of the two magnitudes and then subtracting the two phases. So let's go back and let's just go ahead and try and do that. Let's first take our impedance, which is 4,000 plus J628.3, and let's convert it into a phasor, okay? Let me just erase some of this stuff. We don't need this anymore. This needs to be converted into a phasor. So to find R, we basically need to do R is equal to the square root of 4K squared plus 628.3 squared. And let's see, I'll do that on my calculator. 4,000 squared plus 628.3 squared. And then we'll take the square root of that. That gives me basically 4.05K. I'm kind of rounding here. And then my phi is going to be the tan inverse of 628.3 divided by 4,000. And make sure you're in degrees mode when you do this, otherwise it's going to spit out a value in radians. So I will take the tan inverse of 628.3 divided by 4,000. And I get 8.926 degrees. 8.9, let's just round up to 3 degrees. Okay, that right there is my impedance phasor, okay? These two values here. So I can write it as 4.05K, my impedance, 4.05K, angle 8.93 degrees. So now I can use Ohm's law because I know over here, I of t, or in this case, it's actually just going to be big capital I, right? I wrote it over here as V is equal to I times Z in phasor form. So my big capital I phasor, because I'm going to get a phasor out of this, you know, quotient here, is going to be my voltage, which is 5 angle 0 divided by 4.05K angle 8.93 degrees. All right. That's going to be equal to 5 over 4.05K angle, and I can take the difference between my two, 0 minus 8.93, so it's going to be negative 8.93 degrees. What does it mean for us to have a negative phase? It just depends on whether it shifts the value forward in time or backwards in time. We'll talk about that pretty soon where we talk about leading and lagging and what it means, but I haven't talked about that quite yet. But let's take this 5 divided by 4.05K. That's going to give me 1.23 milliamps. Okay, so my I phasor is equal to 1.23 milliamps, or sorry, 1.23 angle negative 8.93 degrees milliamps. That right there is my I phasor. How would I get this into I of t, or how would I get this to be a time domain function? Let's go ahead and move this over. All I have to do is basically take the exact same omega t that I used for the voltage, because I said, right, my frequency isn't going to change. So I can take this same omega t, this same sign, and I can just slap my new magnitude, which is here, and my phase right out here, and I will be done with this problem. So I can write I of t for this problem is going to be 1.23 times the sine of omega t, which is going to be, I'm just going to write it as omega t so I can, save space, minus 8.93 degrees milliamps. And that right there would be the answer to this problem. Find I of t. That is the solution. So that's the process. We can go ahead and convert over to the impedance domain, convert things to phasors, do the math, and then spit it back out to ourselves in the time domain. So hopefully that problem makes sense. I know it's the math is a little bit heavy. We start getting into complex numbers and things that people don't typically like, but I hope that we can do enough problems that you'll get comfortable with them. And if you have any questions, please feel free to ask. And I'm going to go ahead and wrap this one up. And in the next video, next couple of videos, we're going to do a KCL example. So just make these concepts even clearer. Okay? I'll go ahead and end it right here.